So today's lesson is the last one on proof by induction. We're going to just sort of look at three different types of induction things that might occur. Again, I can't possibly cover all induction problem types, but I'm trying to give you some variety. We've done a couple of lessons where we've really got in a sense of how induction works, and we've looked at some tricks about how you can address certain types of induction problems. But I'm just now going to do three new ones. So first of all, we have this inequality type induction. The question is to prove that 2 to the negative n is less than 1 over n for all n in z plus. So now again, we start by creating a name for this statement. So let Pn be, and then it's just going to be 2 to the negative n is less than 1 over n, and the statement does not have the for all n in it. And now consider P1, and the reason I'm starting with P1 is because I'm dealing with n in z plus, so 1 is the first number there. So the LHS of this 2 to the negative n less than 1 over n, that's 2 to the negative 1, which is going to be 1/2. And the RHS is going to be 1 over 1, which is 1. And we can say 1/2 is less than 1. Therefore, P1 is true. Okay, so we proved P1. Now we say assume, and I like to do it this way, there exists a k in z plus such that pk is true, i.e. 2 to the negative k is less than 1 over k. We will show pk plus 1 is true, i.e. 2 to the negative quantity k plus 1 is less than 1 over k plus 1. Okay, so when you're doing an inequality proof, you have to treat the inequality a little bit aggressively. So let me show you what I mean by that. So LHS equals 2 to the negative and then quantity k plus 1, which I'm going to write as 2 to the negative k times 2 to the negative 1. Because after all, negative k and then minus 1, when I put those together, I get negative quantity k plus 1, or negative k minus 1 if you want to write it that way. Now I want you to notice that the 2 to the negative k part, that is from our assumption that it's going to be less than 1 over k. So what I'm going to do is I'm going to write this as less than 1 over k times 2 to the negative 1. So all I've done is replace this part with this part, but it was in an inequality that I was able to do that replacement. They were not equal, so I need to make sure that I am using this inequality and substituting and making the inequality true. And let me say by assumption. Okay. Therefore, 2 to the negative quantity k plus 1 is less than 1 over k times 2 to the negative 1. And now we're going to go work with that 2 to the negative 1. So we're going to say this is still equal to 1 over k times 1 over 2. In other words, 1 over 2k. Now I want you to notice that this denominator here is 2k. What I'm trying to get is k plus 1. So I need to make an argument that 2k, the denominator there, is bigger than that denominator there. So notice that for all k, and again, it's in z plus that we care about, we know that 2k is greater than or potentially equal to k plus 1. And the reason I need the equal to is because when k is 1, 2 times 1 is 2, and 1 plus 1 is also 2, so there's an equal to. But if k is anything bigger than that, then 2k, when you double something that's bigger than 1, then it's bigger than just adding 1 to that. So if you have, like, if k was 2, then it'd be 4 versus 3, etc. So I don't need to make an argument about why that's true. You could, I suppose, but therefore 1 over 2k is less than or equal to 1 over k plus 1, again, for all k in z plus. So this is the thing we really wanted to make an argument about, comparing the 1 over 2k to the 1 over k plus 1. And we've got it in an inequality with an equal to potentially. Now, if I think the logic all the way through, I can go back and say, finally, 2 to the negative quantity k plus 1 is going to be less than, and then follow this inequality down to here, 1 over 2k, which is then less than or equal to 1 over k plus 1. And this is what I mean by aggressive inequalities. You're going to have to make an argument about an inequality going here, and then very likely another argument about another inequality going to the next stage. So you'll be using the assumption for one of those inequalities and then potentially another argument for another inequality. And if you follow the inequalities, if this is less than this, which is less than or equal to this, clearly I can skip directly from here using only less than without the equal to compare these two. Therefore, pk plus 1 is true. And now we can do our rigmarole. So we showed p1 is true. We showed pk plus 1 is true whenever pk is true. By induction, we showed 2 to the negative n is less than 1 over n for all n in z plus, and we draw our box to celebrate. And so very quickly, I go through the argument again, make the statement, try the left side and right-hand side and show that there's an inequality that's true. And then when you're doing of course, the assumption and whatever, and when you're doing the pk plus 1 proof, you're going to have to be aggressive with your inequalities. What I mean by that is there may be more than one inequality involved. Do a straight replacement of using the pk, and then you may have another one that you have to make an argument about later on. And then if you follow the inequality all the way through, you will recognize that the thing you were trying to prove is going to be true. And that's the end of that one. Let's look at another one. All right, so in this example, we have a sequence that's defined by u1 equals 1 and u sub n plus 1 equals 2un plus 1 for all n in z plus. So this is a recursively defined sequence. And we want to prove that this explicit formula, un equals 2 to the n and then minus 1, is true for all n in z plus. So we're taking a recursively defined sequence and proving that we have found the explicit version of that sequence. So again, we will start with let Pn be un, u sub n equals 2 to the n minus 1. That's the statement we want to prove. Consider P1. Because after all, the domain is z plus. So P1, u sub 1 is equal to 2 to the 1 minus 1, which is equal to 1, which is given above. And what I mean by that is that that's what we were told over here, that u1 is equal to 1. And the un formula that we're trying to prove also gives us 1. So that's okay. Therefore, P1 is true. So now we assume there exists a k in z plus such that pk is true, i.e. u sub k is equal to 2 to the k minus 1. We will show pk plus 1 is true, i.e. u sub k plus 1 is going to equal 2 to the k plus 1 minus 1. All right, so consider pk plus 1. LHS equals u sub k plus 1. Now, I want to make it look like this, but what I'm going to do is I'm going to take the u sub k plus 1 and I'm going to sub it into the originally defined sequence. I'm going to use this recursive formula. I'm going to plug it in over here. So it's equal to 2u sub k plus 1 by definition. Right? That's what we were told, was that u sub n plus 1 was defined by definition as u sub n plus 1 equals 2u sub n plus 1. So I'm using this formula and using it to replace the u sub k plus 1 again by definition. So now I want you to notice that we've enabled ourselves to use UK, which allows us to take the assumption into account. So that took us from u sub k plus 1 into something involving UK, which then is the assumption. So therefore, u sub k plus 1 is equal to 2 UK plus 1, which is equal to 2. And then I'm going to substitute 2 to the k minus 1 plus 1 by assumption. So I use the definition, and then I use the assumption. And now all I got to do is simplify this. So u sub k plus 1 is going to equal, well, I distribute the 2, and then I add 1. So 2 times 2 to the k minus 2 plus 1. And of course, 2 times 2 to the k turns into 2 to the k, 2 to the k plus 1. And then the minus 2 plus 1 turns into minus 1. And that, of course, is equal to the RHS of the statement we were trying to prove. In other words, this statement. So that was the LHS, that was the RHS. And so we've now proved that PK plus 1 is true. Therefore, PK plus 1 is true. Okay, so here's our rigmarole. We showed P1 is true. We showed pk plus 1 is true whenever pk is true. By induction, we showed u sub n is equal to 2 to the n minus 1 for all n in z plus. And that's in our proof. And again, quickly to point out what happened here. So we obviously did the P1 statement, and then we had the assume and the thing we're trying to prove. And the thing we're trying to prove has a u sub k plus 1, which allows us to use the recursive definition of the sequence. That's how we're going to get from k plus 1 down to k, so we can take advantage of the thing we assumed was true. So you have the use of the definition and the use of the assumption after that, and then of course everything works itself out. So if you've got a recursively defined sequence, you hope it's defined with n plus 1, but it could just as easily have been written something like this: u sub n equals 2 u sub n minus 1 plus 1, and then you would just adjust when you use u sub k plus 1, that matches with the n. So this becomes k plus 1 minus 1, which becomes k, and therefore would have worked okay as well. Let's do one more. All right, so prove that a convex n-gon has 1/2 n times n minus 3 diagonals for all n greater than or equal to 3. So let P sub n be a convex n-gon has 1/2 n minus 3 diagonals. And I'm not going to write for all n greater than or equal to 3. Now, because it's an n-gon, I don't have to specify that n is an integer because the n represents the number of sides of this polygon, so it has to be a positive integer. In fact, it has to be greater than or equal to 3 because the polygon with the fewest sides is a triangle, and therefore n equals 3 has to be the very first one. So we consider P3, because that's, after all, where we start. A convex triangle, which, of course, has no diagonals. And 1/2 n minus 3 equals 1/2 3 minus 3, which is equal to 0. So P3 is true because, after all, we just showed that the formula gave us 0 diagonals. And, of course, a triangle has no diagonals, so you don't have to worry about that. So now we assume that PK is true for some k in Z plus. That was a minor error. Here is a correction. It should say for some k greater than or equal to 3, because that's the way this was, the domain of this problem was defined. I.e., a convex k-gon has 1/2 k minus 3 diagonals. We will show pk plus 1 is true, i.e. a convex k plus 1 gon has 1/2 k plus 1 k plus 1 minus 3 diagonals. And, of course, that simplifies, i.e. 1/2 k plus 1 k minus 2. Okay, so this one is going to require a diagram of a partially completed polygon. So here we go. I'm going to draw a partially completed polygon. Okay, and then dot, 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 dot. Okay, so this is the n-gon, the k-gon. Which has a 1/2 k plus 3 diagonals, which I'm not going to draw, not drawn. Now what I'm going to do is I'm going to add in a new vertex. So using a different color, in red, we add a new vertex. And I have to do this in a clever way. I'm going to take two pre-existing points, two pre-existing vertices, and create a polygon by adding an extra vertex, by adding it in between there and making sure that I maintain the convex nature of the polygon, so I don't go way over here or way in here or anything like that. Add a new vertex, and now we find all the new diagonals created. So what I want you to notice is that a diagonal is created when you take two non-adjacent vertices and connect them. So, for example, these two vertices are adjacent, therefore they are not a diagonal. But say this vertex and this vertex are not adjacent, so that creates a diagonal. So these two previously adjacent vertices are no longer adjacent once I've created the extra vertex. And there's only one pair of those where that's true. So there's one old side of the polygon, of the k-gon, I should probably say, of the k-gon, is now a diagonal of the k plus 1 gon, because there's a new vertex between them, or the new vertex is between them. Okay, so that's one diagonal. And then this new vertex now will connect to all of the previous old vertices except for this one and this one. So it will connect to that one and that one and that one and that one and that one. And those are all new diagonals because this vertex did not exist before. So how many new diagonals will I create? Well, I will not connect to this one, and I will not connect to this one, but all the other vertices I will connect to. So the new vertex connects to all but two of the previous vertices of the k-gon. Of the k-gon. In other words, k minus 2 new diagonals that way. From the new vertex. Let's put it that way. Okay, so I'm going to have to go to the next page to finish this off. But my argument again was that whatever diagonals I had before are still there. And then I've created one new diagonal that connected the two previous vertices that used to be adjacent, now are no longer adjacent. And then the new vertex now connects to k minus 2 other vertices because it doesn't create a diagonal with the two now adjacent vertices, but all the other non-adjacent vertices it does connect to. So that's k minus 2 plus the extra 1. So it's a total of k minus 1 new diagonals. All right, so I'm going to go to the next page. So I've summarized the information I needed from the previous page, which was the convex k-gon had 1/2 k minus 3 diagonals. That's what we assumed. A convex k plus 1 gon has 1/2 k plus 1 k minus 2 diagonals. That's what we're trying to prove. And we have now found k minus 1 new diagonals when adding one vertex to the old k-gon. So the total number of diagonals of the convex k plus 1 gon is 1/2 k minus 3 plus k minus 1. Now this part was by assumption. And this part is the new diagonals. And now it's just a matter of simplifying this. And so I'm going to go ahead and distribute the k minus 3, and then 1/2, etc., and then try to factor. So here we go, which is equal to, let's go with 1/2 k squared minus 3/2 k, and then plus k minus 1, which is basically, I'm going to combine like terms first. 1/2 k squared minus 1/2 k minus 1, which I will then factor out of 1/2. So 1/2 and then k squared minus k minus 2, because 1/2 times -2 is -1. And I can factor that k squared minus k minus 2. It's a monic quadratic, so it's easy. K plus 1, k minus 2. Therefore, p k plus 1 is true, because after all, this was the number of diagonals I was expecting to be able to get. So now we do our little rigmarole. We showed, well, I actually showed P3 is true, not P1. We showed PK plus 1 is true whenever PK is true. By induction, we showed a convex n-gon has 1/2 n minus 3 diagonals for all n greater than or equal to 3. And that is the end of the proof, and that is the end of the lesson.